Hi, Professor Gassimi here. For this component of the lecture, we're going to be doing a tutorial and touching on some of the natural language processing topics that we discussed in the course. I'd like to mention a couple of logistical items about this tutorial. The tutorial contains embedded within it an assignment that you will need to complete if you're part of the class. There are a couple of things that you'll want to pay attention to if you're submitting this as part of the assignment. The first one is that here at the top, you'll want to insert your name. And I'm allowing you within the class to collaborate with a person when you submit your homeworks. Those homework partnerships should be paired. So if you're going to partner with another person, that person has to partner with you, and your names have to match across your assignments. If you've partnered with someone, it's okay for your answers on the homework to be identical. It's not, of course, okay for your answers to be identical with anyone else in the class when you've partnered. Another quick logistical note about this: when you do your partnership with a student on one assignment or another one of your classmates on an assignment, you can't partner with that person for the next assignment. I'm doing it this way because I would like you to get to know more than one person in the course of this semester. So you can partner as many times as you want, but just know that for any given assignment, you can only partner with one person once. Okay, so the goals of this assignment are to familiarize you with regular expressions, text normalization, edit distance, and n-gram language models and smoothing. These are exactly the things that we ended up covering in the lecture. But here, we're going to be doing a mixture of tutorial exercises with me, and then some learning exercises where you will try to complete certain tasks on your own in the Python notebook and submit it to me as your homework assignment. For those of you who are going to be pulling this repository for the first time, I want to note that before you start, you should pull the latest version of the course materials and copy the contents of homework 1 into the corresponding directory within your submission folder. That way you can push that folder once you've completed your learning exercises, and it will be synced to the course repository for grading. Also, please don't forget to create and attach to a virtual environment and install what's shown in requirements.txt, which I've included here. Okay, let's get started with the first piece of this tutorial. Before we can perform any text analysis, we need to collect some text to apply our analysis to, right? Well, one excellent resource for this, for getting free text data, is a website called Project Gutenberg. I'd like to open this here so that you can see it. So Project Gutenberg is this wonderful resource of 60,000 free ebooks. And it's totally searchable. You can come up here and you can type in the name of an author that you care about. Let's put Kant, for example. And you can get access to all of Kant's works, such as the Critique of Pure Reason. You can even get interesting facts like on the number of downloads that have happened for these books. The books are available in a variety of formats too, as you can see. For most NLP work, the format that you care about is plain text. So you can see I can click this and I can get access to the plain text version of Kant's work. So let's start this tutorial by importing Python's request library so that we can actually pull the data from Project Gutenberg, some text data from Project Gutenberg, onto our local machine. So this request library here is a really powerful tool that if you're not already familiar with it, you really should become familiar with it if you're going to be dealing with any kind of data that's on the web. So after we've imported it, we can specify the web address of the text that we'd like to pull from. In this case, this is a book from Bertrand Russell's The Problem of Philosophy. And we can get the data by running this particular command. And what you can see here is when I make my request for the data from the website, Project Gutenberg returns a status code of 200. and places the text data, which I've shown a sample of here in the printout, in a variable called r.text. Now this status code, I'm printing it here because it's the server's way from Project Gutenberg's side of telling us, hey, that's fine, I'm going to give you the data that you want. And if you had requested a text resource from Project Gutenberg that didn't exist, you wouldn't actually get that status code of 200. So let's, for example, request here together a book called I don't think you have this book.text, which hint doesn't exist. If we run these two lines within the IPython notebook, you'll see that we get a server status code of 404. And this status code basically is the server's way of telling us it was not found. There is no text file called I don't think you have this book.text. I'm pointing this out because if you want to collect your own data from the internet for the project as well as for this assignment, you'll want to pay attention to these server status codes. There are some instances where, for example, servers may refuse connections to you and not give you the data that you're requesting, and you can usually find out why by looking at what these status codes are. For your reference, if you want to learn a little bit more about status codes, I've included a link here. I'll just open it so that you can see it. It's basically a reference for what each of the status codes that you get back from the web page means. Okay. So we've talked a little bit about collecting data from the internet. Now let's talk about regular expressions. As we discussed in the lectures, a regular expression is a compact programming language, and it's specialized for enhanced text search. The way we use regular expressions is with the re library, which comes standard with the Python programming language to analyze text and any other kind of string objects that we're interested in. So let's start by importing re, and then let's specify a regular expression philosophy and search the text that we extracted earlier, which was Bertrand Russell's book. And we're going to print the match that we found for our search query, philosophy. Not surprisingly, we ended up finding it within Bertrand's book. And it was found at the following character span. So starting at character 764, we found the match for the term philosophy. Now, this above example finds the first instance of the word philosophy in the book, but for some purposes, we may want to capture every instance where the search term was mentioned. We can do this using find iter, like we discussed in the lectures. So coming here to these next two blocks within the code, we can run these, and what we can see is that 72 matches for the word philosophy were identified. And we have the indices for each of these. Let's take a look at this object. This first one says that, as you recall from the previous one, starting at character span 764, we found the word philosophy. We found another one at the character span starting at 1833, and so on and so forth. Now, 72 matches for the term philosophy seems a bit low. So let's update the regular expression so it's not as sensitive to capitalization. The way we're going to do that is by, instead of writing out the word philosophy, we're going to include parenthesis and say it can be either lowercase p or uppercase p when we're searching for philosophy. And let's run this regular expression now and see what the results are. Well, now we found 81 matches, and if you just I've only printed the matches here just to keep things clean. You can see there are some instances where it's uppercase, and there are some instances where it is lowercase. So if that makes sense, it looks like the regular expression did what we were asking for. And I still feel like 81 matches is still not that much, so maybe we should make this even more general by seeking out the terms that start with the word philo, followed by an arbitrary number of A to Z characters. Well, the way we could modify a regular expression to accomplish that is we can keep this first thing. Hey, it can start with a capital P or a lowercase p. It needs to be followed by the characters H, I, L, and O. And then it can have a character A through Z, but as many of these as we want, which is what sort of the plus means. We can have one or more of these characters. So let's run this regular expression and see what we find. Okay, great. Now it says we found 154 matches. And if we take a look through some of these, we can see there's philosophy, philosopher, and felonious. Well, actually, if we count the number of distinct terms that show up, I've done that down here, you can see that philosophy is the most common one. That's the 72 we saw the first time. But there's a bunch of these other terms that sort of show up as well when we ran the regular expression. And one of them that is a little bit problematic is felonious, which is a character, a human character that shows up in the works of the philosophy. So we probably want to modify a regular expression to remove felonious. And the way we're going to do that is using something called negative look-ahead. Negative look-ahead basically says, hey, go ahead and grab all the results, but then if you see this particular piece of the result as you're stepping through, if you see a match for this, exclude it. So let's read this regular expression together. Match anything where I see an uppercase or a lowercase p, followed by HILO. And then if you see anything that matches NOUS after that, so that would match Philonous, exclude those, so throw those away. Now for whatever's left, take an arbitrary one or more A through Z characters and fetch those for me. So if we run this particular regular expression, we now find 151 matches. And if we come down here, you'll notice that, hey, Philonous is gone. So we've done it. Okay, so we've completed the tutorial component of this assignment. Now what I'd like to do is step you through what you will need to do on your own as part of the learning exercise. I'm really curious how Bertrand Russell used these various philosophical terms we just pulled together in his sentences, and how Bertrand's language more generally compares to Friedrich Nietzsche and the other philosophers. And so what you're going to be doing in this assignment is helping me accomplish that. You will be starting by downloading the data using Python's requests library, which we already discussed, and you're going to collect Friedrich Nietzsche's book, Beyond Good and Evil. You'll be inserting your code to do that here in this block. And by the way, anywhere within not only this learning exercise, but learning exercises that happen in subsequent assignments, anytime you see this green block here is where you're going to want to insert your code for the graded part of the assignments. And I'd also like, anytime you've written some code, to write a couple sentences reflecting on the code you wrote. You can comment on what it does. You can give a discussion of the results if there are some. Things that help clarify anything that you wrote or displayed or printed out in your code. After you've downloaded your data, you'll be doing some very basic text cleaning using regular expressions. So specifically, you're going to replace the various forms of whitespace that appear with a single whitespace character. You're going to cast all the text to lowercase. You're going to replace common abbreviations with their full names. For example, it's with it is. Please note here that you don't actually have to replace all of these. So you don't have to do it's, don't, and haven't, and absolutely every abbreviation under the sun. Just choose 10 or so that are common and go ahead and replace those just so that you can show to me that you understand how to do it. Okay, just as we did above, you'll insert your code here and any interpretation or comments on what you did in the red text below. Okay, so after you've performed some of the basic text cleaning on the book, you're going to be building a sentence extractor. You're going to write a regular expression that extracts complete sentences containing any matches from the regular expression that we wrote together earlier. You remember this regular expression from the tutorial part of the assignment? Well, you're going to take this and you're going to say, if I see this match, I want to grab any complete sentence that contained this match. You're going to apply this regular expression to the Beyond Good and Evil book that you pulled, the Problems of Philosophy book that we pulled together, and a work of philosophy that you choose. And you want to show a couple of example sentences from each. You'll write your code here and again kind of print your interpretation. After that, you're going to perform sentence tokenization, again using a regular expression. That is splitting the sentences that you collected in the previous component into a list of individual words, tokenize the text of all 3 of the books completely using that regular expression, and then store your results as a list of lists and print the last word of the last sentence. And in the last part of this homework, or the last part of the first learning exercise, you're going to be comparing the works. So you'll use Python's matplotlib library to compare the distributions of the most common words that show up in each of the books. And I want you to comment on any interesting statistical similarities or differences you see between the distributions. You should tell me if, for example, you see Zipf's law show up. What are the most common words when you ignore some of the terms like the, and, in, etc., and any other kinds of interesting observations that you see when you compare the works of the philosophers. Okay, so in the second part here, we're going to be speaking about text normalization. And as you recall from the lectures, text normalization is an essential preliminary step to any natural processing pipeline. So to begin, let's do the tutorial component of this by re-importing the problems of philosophy. Okay, and now let's try doing some tokenization. Well, as you saw in learning exercise 1, or as you will be doing in learning exercise 1 on your own, tokenization can be performed through the use of a regular expression. And familiar with regular expressions is really important for your NLP toolkit. It's especially if you're going to be doing anything related to extraction from text, you really want to get good at regular expressions. But for basic kind of tokenization work, you actually probably won't use regular expressions in reality. There are lots of actually easier tools to use for basic tokenization work. And one of those is Python's replace function, which is built right into strings. And you can see here, I can take my text and I can just run a replace to say, hey, take all the /r/n characters, these are the line breaks, and replace them with spaces. And I can sort of daisy chain these to replace any single /n characters and /r characters as well. And if I print the results of Bertrand Russell's The Problems of Philosophy, both before and after, I can see here that in the before, there were character returns. That's why there's white space here. And then after, I've eliminated those from the text. So, hey, that seems to work. And I want to point out here as well that replace doesn't require you to import anything. It's built right into Python strings, so you don't have to import any libraries to use it. Python actually in general has a lot of useful string manipulation methods. You can learn more about those here. I've included a hyperlink. You'll see that, for example, you can find the index of an occurrence within a substring. You can find if it's a decimal, if it contains a digit, if it's lowercase. There's a whole bunch of very useful things that will be great for your NLP toolkit. Okay, great. So let's carry on here. The only other real tool we're going to need for basic tokenization of our text is the split function, right? So, well, what did we just do together? Up here in the tutorial, we replaced the new line characters. Well, now let's take that clean text and let's just split it every time we see a period so that we can create the sentences, okay? And if we take this and we print sentence 10, the tokens in sentence 10, you can see I get a pretty clean set of tokens here from Bertrand Russell's The Problems of Philosophy. Now, this pre-processing that I've shown is mostly for illustrative purposes. You could use it if you wanted to do some very basic kind of NLP things, and the whole point is to help you become familiar with how tokenization works. It's just splitting based on when you see the presence of white space or some other kind of indicator that you might care about. The tool that you would probably use for most of your NLP needs is NLTK for tokenization. So I've got an example down here of how we can use it. You can import NLTK by simply calling import. And this block of code down here only handles the connection to a server to download the NLTK's tokenizer. So you don't really need to focus on understanding this as much, just to know that it helps you download the tokenizer that with NLTK. If you run this line and you get the true down here, it worked. And we can test out the NLTK tokenizer on a tricky sentence now. Like, let's specify, for example, at 8 o'clock on Thursday morning, Arthur didn't feel very good. He drove to a store in New York at 100 miles per hour. He wanted to obtain some Kool-Aid. It cost $10.89. So if we want to tokenize this text using NLTK, we can do it in one line, as we show here, and then print what some of those tokens are. And if you look at it here, it's actually pretty good, right? I mean, so it understood that miles per hour should be together. It understood that despite the hyphen, that o'clock should be one word. It's not perfect. It didn't understand, for example, that New and York should probably be together. And it also didn't catch that this $sign should probably be combined with the 1089 because this is a monetary figure, right? So NLTK's tokenizer is great. It's not perfect. This is actually part of the motivation why we talked about some of the other contemporary techniques, such as byte-pair encoding. Okay, so the last thing we'll want to talk about in this tutorial component is that, we've done this tokenization at the level of, a sentence, but there's ways to tokenize things into full sentences as well. So I might care about having a collection of sentences instead of a collection of words. There's another NLTK tool called sent tokenize that you can run here, and it will split the above example into, at 8 o'clock on Thursday morning, Arthur didn't feel very good, followed by the next sentence and the next sentence and the next sentence. So I think it's pretty important for you to know about NLTK because I anticipate that for some of your project work, you'll probably be using it for your tokenization. I do want to note here that, or re-emphasize that it isn't perfect. And it's the lack of perfection of these methods is part of what motivates some of the data-driven approaches like byte-pair encoding. And actually, speaking of byte-pair encoding, the work that you'll be doing in learning exercise 2 on your own is to implement the byte-pair encoding algorithm and to tokenize the problems of philosophy that we downloaded earlier together. Now remember, byte-pair encoding is very sensitive to the size of our corpus. And so one thing that I'm going to ask you to do is download 5 books from Bertrand Russell and 5 books from Nietzsche, and to use that combined larger corpus to implement to use that as the training corpus data when you're implementing the byte-pair encoding algorithm. I'm then going to ask you to evaluate that byte-pair encoding algorithm for a number of different sort of settings of the parameters of the byte-pair encoding algorithm and as a function of how we change things about the training corpus. Okay, so now let's talk a little bit about edit distance. Well, as you remember from the lectures, edit distance is just a way to measure the similarity between different sequences of text. Our goal in this section will be to compare and contrast some of the different measures of edit distance that exist so that you have a better intuition for how to use them depending on the problem you're trying to solve. So let's start by importing the text distance library written by Graham Voronov, and you can see this documentation for the text distance library here on the web by clicking the link. This gentleman, Graham, has implemented 30 or so of these algorithms in Python and has included links to the different algorithms that he implemented. The reason I linked you to this repository is because If you decide you want to make a contribution to the text or edit distance kind of field, or you want to do some interesting work with edit distance either for your project or on your own, you can come here to the algorithms folder and you can get some nice Python implementations of each of the different kind of edit distance functions. You might recall, for example, the Levenstein distance that we discussed in class is implemented right here. Okay, so we've imported this text distance library. Now, what I'm going to do is I'm going to define just a very simple, there's many methods that exist within Graham's text distance library. So I've defined a very simple function here that takes in two strings, the method we want to use to get the distance for, and just prints the distances. So let's go ahead and get the distance between test and text, test and text, and test with some white space. And let's go ahead and compute the Levenstein distance for those three things. Now, as you can see from the results here, there's clearly a difference between the three. And let's sort of step through and try to understand where these differences come from. Recall that in the lecture, the Levenstein distance counts the total number of insertions, deletions, and substitutions that are required to transform one string into another. And the cost of the edits is always 1. So as I'm showing above, moving from test here to test, well, there's no edits to perform, right? I mean, it costs nothing to move from here to here, so it's 0, obviously. If I wanted to move from test to texts, what would I need to do? Well, I'd need to swap out this x for an s. I'd probably want to delete this s, and so the cost is 2. And if I wanted to turn test into this test, I would need to delete these 3 white space characters, and that's why the Levenstein distance is 3. Okay, now this above example is meant to highlight that the assumptions of edit distance has consequences for their estimates. And depending on the problem we're trying to solve, we might want, for example, this test here to be more similar to this than this is to this, right? It just depends on sort of the parameters of the problem we're trying to solve. Usually when you're dealing with alignment problems, for example, knowing or substring alignment problems, you'd want this and this to be more similar than this is to this. Okay, so on that note, let's explore the performance of 3 other edit distance measures, the Hamming distance, the Needleman-Wunsch distance, and the Smith-Waterman distance. So using the same function that I defined above, I'm just going to enumerate the distance measures I'm interested in trying. I'm going to cycle through them, and I'm going to print the distances for the 3 strings that we already described. Okay, so here I have them. I have that the Hamming distance between test and test is 0, test and text is 2, test and test is 6. And I have here that the Levenstein distance is 0, 2, and 3. The Needleman-Wunsch distance is 4, 2, and 1, and the Smith-Waterman distance is 4, 2, and 1. Okay, so let's step through these results together. First, we notice that the Hamming distance between test and test is 6. And 6 is even higher than what we observed for the Levenstein distance. To understand why this is the case, we can refer to the definition of the Hamming distance. Hamming distance between 2 strings is the number of positions at which the corresponding symbols are different. Okay, so what you would do to understand that is you would basically say, assuming that this guy had a bunch of white space on him, and then I just overlaid test on top of test, and I counted, one for one, what the differences were, how many of the characters would be different. Well, they'd be different in 6 of the positions, right? Because the ending T here in test would overlap with this starting T test, but otherwise every other character is going to be different. So there's 6 positions where it's different, and therefore the Hamming distance is 6. So again, Hamming distance is just measuring this minimum number of substitutions, right? Now, what's more mysterious here is this Needleman-Wunsch and this Smith-Waterman distance. You can see that the Needleman-Wunsch says that the distance between test and test is 4, as the Smith-Waterman method does as well. And this is kind of weird at first, right? You're like, well, why is the distance between these two things? Shouldn't that be 0? Well, it's not 0 because these distance metrics are each quantifying a definition of distance differently. In the case of Needleman-Wunsch and Smith-Waterman, they're actually providing an alignment score between the two sequences. So the reason that you have a 4 there is because it's saying that 4 out of the 4 characters are aligned in the case of text. So T matches with T, E matches with E, S matches with S, and T matches with T. So it sort of is higher number in this case is a good thing, whereas lower number is a good case in these two. And understanding this is important if you want to compare, for example, across distance metrics. Okay, well, this still doesn't explain why there's this big difference between the Needleman-Wunsch's distance on test and test versus the Smith-Waterman distance on test and test with some spaces. So to understand maybe what's going on here, we can do that by experimenting a little more. Let's take those two methods, Needleman-Wunsch and Smith-Waterman, and let's add more and more white space to the second string that we're going to be checking the edit distance against. And let's see how both of the methods react. Okay, well, it looks like with the Needleman-Wunsch distance, the more white space we add, the further we kind of drift test away from the initial position of this particular test, the less positive this becomes. Okay, so in other words, it grows more negative as the absolute distance between the two strings increases. So in this way, the Needleman-Wunsch algorithm is similar to the Levenshtein distance algorithm. The difference here is that Levenshtein is using a static penalty, a cost for any mismatched letters, when Needleman-Wunsch is using a weighted version that considers the points you get from a match and a mismatch a little differently. So that's basically the difference between the two. This Smith-Waterman, though, as you come and turn your attention to this now, notice that it doesn't matter sort of how many white spaces I add here. The edit distance is always 4 in this case. And the reason it remains 4 is because this substring test overlaps perfectly with this substring test in both cases, regardless of the amount of white space. And this search for the largest possible substring is, in this particular edit distances case, what Smith-Waterman is producing. I want to note here that both Smith-Waterman and Needleman-Wunsch are primarily used for alignment. I'm exposing them to you here so that you're kind of familiar with them and you can poke around with them more in your own time. We won't be discussing text alignment too much in this course, which is why I thought it would be great to describe it here in the tutorial. Okay, now there are not just edit distance measures that look at characters, but as we described in the lecture, you could think about an edit distance in terms of doing operations at the order of words too, right? So let's take a look at the Jaccard index as one distance measure, which is basically the size of the intersection of the token sets divided by the size of the union of the sample sets to measure the similarity between two pieces of text. So for example, here I have 3 sentences. I have sentence number 1 is, the fish was delicious and it made quite a dish. Sentence number 2 is, the fish on the dish was made quite delicious. Text number 3 is, Joe eats crabs. Crabs do not taste good. So what I can do is, again, using the same get distance function I did above with some print statements just to create a pretty output, I can compare sentence 1 to sentence 2 and sentence 1 to sentence 3. And what would I expect? Well, I would expect that based on what the Jaccard index is measuring, which is the intersection of the token sets, this should be higher. The distance between text 1 and text 2, as measured by Jaccard, should be higher than it is between 2 and 3. And in fact, it is. So you can see here, the fish was delicious and it made quite a dish, and the fish on the dish was made quite delicious is 0.78 compared to 0.39 when we compare the first sentence with the one about Joe eating the crabs. Okay, so for the learning exercise on this component, this should be pretty straightforward. All I'd like you to do is take the Levenstein distance metric, which remember just assigns a cost of 1 for every miscomputation, and update the Levenstein distance code here, which uses some dynamic programming, so that when a person makes a white space-based substitution, you only assign half of the normal penalty. And that's all you'll need to do for this third part of the assignment, as well as obviously inserting comments on your results. Okay, now the last part of the tutorial today is about n-gram language models. So here we're going to be covering how we build language models that use n-grams. And just as a reminder, an n-gram is just a contiguous sequence of n items from a given sample of text or speech. And so let's begin this section by defining a function that's going to generate the n-grams from our data using NLTK, and using it to extract n-grams for n ranging from 1 to 5. So what we're going to do here is we're importing NLTK, and from NLTK.utilities, we're importing this n-grams function. And the n-gram extractor is simply going to run the n-grams function from up here, and it's going to run it after we do the word tokenization. And we already tried out this word tokenizer earlier together when we were in the earlier part of the tutorial, so this should be familiar to you. And this function, extract word n-grams, obviously takes some text data. It takes the number or the size of the gram that you want, and it goes about generating the n-grams. So we can define some example text here. You should probably remember this from the lecture. And we can print out what the different grams look like: 1 grams, 2 grams, 3 grams, 4 grams. And if we do that, you can see here printed an example of some of the 1 grams is a fish keeps 4a. Some of the 2 grams are a fish keeps 4a day, and so on and so forth for 3 grams, 4 grams, and we could make those grams as large as we wanted. Now, you'll notice that n-gram extractor above uses the NLTK tokenizer that we discussed earlier in the assignment. And it also uses the n-gram generator built into NLTK. But I just want to emphasize here that you don't have to do your grams in words. You could do them in characters. And you also, the process of creating the grams is simple enough that you actually don't even really need a library for it. You can do it pretty much in pure Python. That's what I'm trying to show you down here. So for the same text sample that we had in the lecture, this data, you can basically a line come up with something that extracts character level n-grams. So you basically start at the beginning of the string, you step through, and for as long as the gram you want, you step that many characters forward, you grab that piece, you combine it, and you pack it into a list. That's what this little function does. Okay, and so if I run this, you can see I get the 1 grams from the sentence, I get the 2 grams, the 3 grams, and the 4 grams, but these are at the character level now instead of at the word level. Now for some classification models, you could think about these grams as like features, right? Features for a machine learning model. You could, at a given point in a sentence, if you wanted to predict something about what's going to happen next in that sentence, you could look at information at both the character level as well as at the n-gram level, or at multiple levels of resolution at the n-gram level for that matter. Okay, we touched on skip grams in the lecture. These are going to be important, not really this week, but they're going to be pretty important for topics we cover later, so I thought I'd introduce them here. I just wanted to let you know that kind of generating a skip gram in NLTK or using NLTK is very simple. It's analogous actually to what we did before. So the skip gram, as you can see here, gives you a fish, so it gives you these two together, but then it does a skip, so it gives you a and keeps. And then it gives you a and 4. And then it gives you fish and keeps, and then fish and 4, and so on and so forth, right? So basically, the skip grams include these, these skipped over terms when it returns the grams. Okay, so now let's kind of wrap this up by talking about, finally, language models. A language model, as you probably recall from the lecture, is any method that assigns probabilities to strings. So let's try to develop a concrete understanding of language models by building a very simple one together. And more specifically, we're going to build a model that tries to predict the next word in a sentence given the last word that we saw. One approach to accomplish this is, as we did in the very simple lecture examples, to simply count each of the unique words and then check for each of those unique words what words tend to follow it. And so let's do that using the extract word n-grams function that we wrote a little bit earlier, collecting all the unique words in the corpus. So let's keep that same data that we used from the lecture. Let's extract the unigrams. And then let's get the vocabulary, which is just the set of unique unigrams that exist in our data. And let's print those out. Well, what do we see here is that there's a total of 40 unique words. And so what we're going to need to do then is have basically a 40 by 40 matrix, is one way to think about it, that represents, when I saw the word also, what was the likelihood of seeing one of the other 40 words happening next? If I saw the word the, what was, how many times did the other 40 words happen after that? And so on and so forth all the way down the line. Now we could do it in a NumPy array, but I actually think it's significantly more intuitive to store these items in a JSON dictionary for reasons that you're going to see here in a minute. So let's initiate a dictionary called counts. And what this counts object is going to be is a dictionary of dictionaries that's going to it's going to provide the count of all the next words after you give it the current word that you're sort of looking at. So by way of example, let's look at the count of all possible next words given that the current word is fish. And you can see here that it outputs a dictionary and says, okay, given that I'm currently at the word fish, I've seen no counts for the word also, no counts for the word the, no counts for a period, and so on and so forth. And of course it's seen no counts because we actually technically haven't counted anything yet. We just initialized that count object. So let's go ahead and do the counts and then recheck the count of words that tend to come after we see the word fish. Okay, now if we look at this dictionary and we say, hey, give me the counts for fish, you can see that scrolling our eyes across this, counts was followed by the word, or fish was followed by the word keeps 3 times. It was never followed by the word cold. It was never followed by the word away, and so on and so forth. And we can pretty conveniently look at how one word tends to follow another by, as I'm showing up here, just giving the name of those 2 words together. And I can get the total number of counts of those 2 words. In this case, keeps followed fish 3 times. That's what that means. Okay, so now that we have the counts of the words, we can convert these to probabilities by simply dividing by the total incidence of the next word for a given set of current words. And so here we're initializing a probabilities object, which is structurally identical to the counts object that we initialized earlier, this one up here, if you remember. So it's exactly the same structure, it's just named differently. And then all I'm doing here is I'm dividing by the total number of objects that fell into one of those little next word dictionaries so that I can get the probabilities. Okay, so now let's check the probability of the next word being keeps, given that the current word is fish, and that probability is 75%. You may recall that if you just come up here and glance through, keeps showed up 3 times, comma showed up once, so 3 out of 4 is 75%, so that verifies that this is in fact correct. And so there we have it. We've built the first data-driven language model. And now let's try to do something fun with this language model, like simulating new sentences using the language model. And we can do that by seeding the language model with a word and then selecting the next word in accordance with the probability given by the language model. So here's what we're going to do. We're going to import a library called NumPy, And all that this library NumPy is going to contribute to this is some mathematical operations that are going to make sampling according to the probability of the next word pretty easy. I've written a little function here, sample next gram from language model. What it does is it takes the probabilities we generated above, it takes a sample token, and it will go about generating and sampling from a multinomial distribution where the probabilities for each of the classes in the multinomial distribution are defined by what you pass in that probs dictionary. Okay, and it will then select one of the samples and return a word to you. So that sounds like a mouthful. I think an easier way to understand it is for me to just specify a given token. Let's say we start with A, and then to run this and see what happens. So let's run it together. So look, so I ran it and I said, given the token A, our language model suggests that the next token should be day. But remember, this is probabilistic. So if I run this multiple times, oh, okay, now it suggested fish. Now it suggested day again. Now it suggested cold. Now it suggested day again. Now it's just a day again. And we can keep running this over and over and over again, and it's going to select words in accordance with the probability that we saw in that training data corpus. Okay, well, that's cool, right? We were able to, given one word, generate the next word in accordance with the probability that we saw in the training data set. Well, we can do super useful things with this, right? Like we could run our model to generate brand new sentences by simply taking this next token that we saw here, making it the given token and sort of daisy chaining that forward as far as we need it to. So this little function here is just my implementation of that. It basically takes a sentence length here. You give it a starting seed token, and then it calls that sample from gram from language model that many times, passing the tokens that are output as an input each time. And daisy chains it all together very easily so that you can print it. So let's run this 3 times and see what happens. So here are 3 sentences, brand new sentences that were generated by our language model on that paragraph of text. This is the machine generated this for us. A cold place, a fish keeps for a cold place. A day keeps best if you put it with an apple. A fish keeps best if you'll be having fish. I want to note here, these are 3 brand new sentences that the language model, this very, very simple kind of lookup table, probabilistic lookup table language model developed on its own. And I really wanted to step you through this so that language models are hopefully less mysterious to you. When you start to work on neural networks, or we build any kind of machine learning based approaches to developing language models, at the end of the day, it's going to be a set of probabilities. And if we want to do a chatbot, for example, it's going to work identically to what I've just shown you here. You're going to run it forward, maybe up to a breaking point, which is a terminating character, and you can use that for language modeling. Okay, so to conclude, what you'll be doing on your own is to come back to our work with the philosophers, is you'll be building a trigram Nietzsche language model and a trigram Russell language model using the 5 books from each of the philosophers you collected from Project Gutenberg earlier. And you're going to generate a conversation between your philosopher models by seeding one of the models with a trigram and allowing it to run until it generates a terminating character, which, a period, a question mark, exclamation mark, whatever. You're going to then feed that ending trigram as the input to the other model to seed it, and then see what it responds. And you're going to pass back and forth, sort of the end of one to the start of the other, and then the end of the other to the start of the other one, back and forth, so that you generate sort of let's say a conversation, if you will, between your Nietzsche language model and your Bertrand Russell language model. You're going to insert your code here and just sort of show some examples of what that conversation looks like. The last thing you'll be doing in the assignment is, you might recall from the lecture, there's something called Laplace smoothing, which is meant to handle, remember the zeros up here? If we come back up here, remember these zeros that showed up so many times? Laplace smoothing, as you may recall from the lecture, is just making sure that those zeros are never just 0, right? They're always 1, if you recall. There's going to be some nuance when you want to handle the Laplace smoothing for this particular problem, because not all of the grams that are going to show up in Nietzsche are probably going to show up in Russell. So you'll have to think about how you're going to share those grams across the two to make sure you don't the language model doesn't fail when it's having the conversation. Okay, the last thing that we need to cover is how we go about doing assessment for not only this assignment, but all the assignments in the course. The assessment always starts with a self-assessment. So after you've gone through the homework and you've completed the learning exercises, you're going to provide an assessment of how well you think you accomplished the learning exercise, either by yourself or you and your partner together. I need you to comment on how well you accomplished what I asked you to accomplish. Don't assign yourself points for things like effort. And this self-assessment will be used as a starting point when I come to grade the assignments. Please note that if you overestimate your grade on the learning exercises, I will deduct a penalty for that overestimate. But if you underestimate your grade, I will not apply a penalty. And if I disagree with you, we're going to take my more generous kind of set of points.